everybody. Okay, so in this video we are looking at the normal curve and the standard normal curve and z-scores. So we should be familiar with the normal distribution at this stage. The normal distribution is a very infamous distribution in statistics. So you can see here, data can be spread out in many different ways, right? All my data can land in the bottom. We say this is skewed to the right. Or most of my data could be to the right hand side. Sorry, skewed to the left. So this is most of my data to the left, so it's skewed to the right. Most of my data here is kind of on the right hand side, so we say my data is skewed to the left. My data could have no distribution at all, could just be jumbled around, or it nearly follows this little bell curve shape here, and this is what's known as the normal distribution. So the normal distribution is a very important distribution in statistics. It is symmetrical with the mean mu, so this is pronounced mu, mu, in the center. So the normal distribution, things that be distributed by normal distribution would be like height, weight, grades. So if you imagine it, right? Like down here, not many people would be very short, not many people would be very tall, right? And most of the population should be within kind of this region here, right? Like the 5 foot, 6 foot area. So that is normal distribution, right? So important things about normal distribution: the mean is equal to the median, which is equal to the mode. It is symmetrical about the means. That means data to the right hand side here. So like the area of the right hand side here is equal to the area of the left hand side of the mean. And yeah, and it's a bell-shaped curve, and then 50% of the value is above the mean and 50% are below the mean. So just something to know about the normal distribution here. It's kind of the transformation of it all. So here's two normal distributions, but in this case I changed the standard deviation. So once I change the standard deviation of a data set, right, if I increase it, it makes it more flatter because it makes my data more spread out. But if I decrease it, it will actually make it more narrower. And then finally here, if I just change the mean, well, I'm just shifting it right or left. Now, it's very rare that we'll be dealing with the regular distribution and regular normal distribution. We will primarily be dealing with the standard normal distribution. So what's the standard normal distribution? So normal distributions can have any mean or standard deviation, as we saw in previous examples, right? So like I can have normal distribution with a mean of 10 and a standard deviation of 5, right? This can make it difficult to calculate the probabilities of an event occurring, right? So say, for example, I had a population of heights and they were normally distributed, and I wanted to find out, well, what's the probability someone is above, 6 foot, right? That'd be quite tricky to do. That is where the standard normal distribution comes in. So we can convert a normal distribution to a standard normal one by using standard units. These standard units are called Z, and this unit basically tells us how many standard deviations is it away from the mean. So the Z-score is essentially how many standard deviations. So if you have a high Z-score, that means your load of standard deviations above the mean. If you have a low Z-score, that means you have a load of standard deviations below the mean. So, again, the main features of a standard normal distribution will be the mean is 0, standard deviation is 1, area under the curve is 1, right? The curve is symmetrical above the mean, so Z is equal to 0. Z-score of 1 represents the score 1 standard deviation above the mean. Z-score of -1 represents the score of 1 standard deviation below the mean. So what's the old mean, right? So we can use this information now to calculate probabilities of any normal distribution. So if we were given a data set that is normally distributed, we can convert to standard normal distribution using the standardizing formula. This formula converts the given units, x units, into Z-score units. So, right, the Z-score is equal to x minus mu over sigma, right? So what's it all mean? Well, Z is my standard score. X is like my observed data point, just my data point in the question. The mu is my mean, and sigma is my standard deviation. So x minus, so my data point minus my mean over my standard deviation. So basically, this would tell us how many standard deviations my data set is above or below the mean. Because essentially what we're doing here is I'm finding the difference between my data point and my population. And I'm finding out how many times my standard deviation divides into it, like how many standard deviations go into it. So that will give me how many standard deviations we are, or my z squared. So it's actually very important when we get this now, because we can calculate probabilities with this. So z-scores allows us to calculate probabilities for normally distributed data. The normal distribution table is in the formulating tables book, and it provides the probability for when my z-score is less than something for a given score. So for example, right, the probability that z is less than 1.65 asks for the probability that a result is less than or equal to 1.65 standard deviations from the mean, corresponding to the area under the curve. So if I look it up, this up in my log tables, right? I don't know if you can see the area here, but this area here, right, is what will be under my log tables, right? So we can only ever calculate probabilities where z is less than something, right? Here, this just represents where my data, the probability that my data is above 1.65 standard deviations. So how do we calculate this, right? So when you open up your log tables to page 36, I believe, right, you'll be greeted with a load of numbers like this. And this is how you read it, right? So these only work for, we can only ever get the probability less than that. So for example, the probability that z is less than 1.3, right? So it's 1.30 essentially. So I go to 1.30, bada boom, bada bing. It's 0.9032. So that is equal to 0.932 or 90.32%. If I want to calculate 1.45, so 1.45, it'd be this one here, 0.9265. Right, so the probability that my data is less than 1.45 standard deviations would be 92.65%. Right. So we're going to do some examples now, and to make note of this, because this is going to come in handy now when this uses our symmetricalness of the normal distribution. So let's have a look here. To calculate the following, to calculate p is less than 1.3. So we draw a sketch. Always draw a sketch. So just draw a sketch. 0 is in the center. So that means 1.3 is to the right of it. And we're calculating the probability that it's less than this. Right. And then what we just literally do is we look it up in our log table. Now we know from up here, right, 1.3, that's equal to 0.9032. So that's just my answer there. What about now if I have the probability that z is less than minus 1.3? So sketch it out. Boom. Doom. 0's there. Minus 1.3 is there. So it's asking me to calculate this, the area less than this. So we need to use now the symmetricalness of my normal distribution, right? Because this little area here would be equal to the area above 1.3 standard deviations, right? And how can I calculate this red area here? Well, I know the entire normal curve is equal to 1. And I can calculate this blue area here from my log tables. I can calculate the area less than 1.3 and then subtract it from 1. And that's what's happening here, right? So if I'm looking for a z-score that is less than a negative number, it will just be 1 minus the probability of it less than the positive. So this would be equal to 1 minus the probability of this blue part, which is just z less than or equal to 1.3. And we know what that is. We look in the table, 0.9032. Subtract it, I get 0.0968. Right, now, what about if I have kind of a compound inequality here, where z is greater than minus 1.3 and less than or equal to 1.68. Again, draw sketch. Always important, draw sketch. So here's 0. 1.65 is here roughly. Minus 1.3 is here. So I am looking for this area here. Well, that will be the area of it less than 1.65. Yeah, so all of that. Then I need to kind of subtract this little part here. And that'll be minus the probability minus 1.3 minus kind of this probability here. So this will essentially be the probability that z is less than 1.65 minus the probability that z is less than minus 1.3. Now remember, if we're finding the probability of less than a minus z square, right, that's just 1 minus the positive. So that'd be 1 minus 0.9032. If you look up 1.65 in the little table here, if you look up 1.65 in your normal distribution table, you get 0.9505. So that'd be equal to 1 minus 0.9032. Subtract from there, you get 0.85373. And that is the area between them two. Now, right, so that's handy dandy if we are given the z-score, right? But what about when we're not and we have to standardize, right? So here we go. The lifetime of sine, cosine, tan batteries are normally distributed. They have a mean life of 86 hours with a standard deviation of 11 hours. Find the probability that a battery will last over 97 hours, right? Will last over 97 hours. So first we need to standardize it, right? The probability that a random battery is more than 97 hours. So we need to standardize this now. So to standardize it, I subtract my mean. My mean here is 86, and I divide by my standard deviation. And my standard deviation here is 11. So I get the probability of my z-score greater than 1. Right? Perfect. Now sketch it out. Boom. Always draw a sketch. Ding. Here's z is equal to 1, and I'm looking for the basically the area above that. So this area here. So, right, in order to calculate this area here, well, I can't never calculate the area above a z-score, but I can always calculate the area below a z-score using my table. So if I just kind of get this area here, right? This area here from my tables, and then subtract it from 1, because remember, the area underneath the normal curve is 1. That is equal to 1 minus the probability that z is less than 1, right? And the probability that z is less than 1, we go to my tables, right? Actually, I don't have it there. But if you go to your tables and look it up, you'll get a number that is 0.8413. So subtract it from 1, you get 0.1587. That means there's a 15.87% chance that a battery will have over 97 hours. Right, and this last one's a fun one, because this one kind of involves a little Bernoulli trial, right? 10 batteries are chosen at random. Find a probability that at most 2 batteries will have a battery life over 97 hours. So we have 10 batteries. What's the probability that at most 2 of them have a mean over 87 hours? So, well, have a battery life over 87 hours, 97 hours. So that would be the probability. That would be the probability that none have a battery life over 87 hours. Probably that 1 have a battery life over 1 has a battery life over 87 hours, and 2 have a battery life over 97 hours. So Bernoulli distribution, Bernoulli trial. So 10 choose 0. So 0 out of my 10, right, are above 97. So it's a 0.187 0.187 chance of getting it above 97. So 0 have that. 10 have the probability that it's not. Right? 10 choose 1. 1 has a problem. 1 is above 97. 9 are not. 2 are above. 9 are not. Put in your calculator, you get 0.797. There'll be a 79% chance that at most 2 batteries out of the 10 are over 97 hours. Right, some exam questions here. So 2023, an online game involves trying to guess 5-letter words in as few attempts as possible. For this game, each player is given a score S, where S is a real number, based on how many attempts it takes them to guess the word. In Ireland, players' scores are approximately normally distributed with a mean of 3.87 and a standard deviation of 0.36. A player selected from random. A player selected random from the players in Ireland. Find the probability that this player has a score less than 3.5. So, what we do is we standardize it. There's a probability that x is less than 3.5. Track the mean. The mean in this case being 3.87. Divided by the standard deviation. Probably that z is less than, right? And if I do the maths here, minus 1.03. So draw a sketch. There's 0. There's minus 1.03, and I'm looking for the probability less than it. Right, so I can't get the norm. So I can't get negative numbers on my normal table. Sorry if I've never mentioned that before, but you can't get negative numbers on the normal table. So this will just be 1 minus the probability that z is less than 1.03, which is 1 minus 0.8465, which is equal to 0.1515. Yeah, 1535. I did 1535. Right. Next one here. In an athlete's competition, there were a number of heats of the 1,500 meter race. In the heats, the time that it took the runners to complete 1,500 meters was approximately normally distributed with a mean time of 225 seconds and a standard deviation of 12 seconds. Find the percentage of runners in the heats who took more than 240 seconds to run 1,500 meters. So again, right, population mean mean time of 225, standard deviation of 12. So it took more than 240. So x is greater than 40. So minus the mean, standardize it. That would be the probability that z is greater than 1.25. Sketch it out. Boom, boom. There's 0. This is 1.25 roughly. I'm looking for the area above it here. And we know this will just be equal to 1 minus the probability that z is less than 1.25. Put that in a calculator. We get 1 minus 0.8944, which is equal to 0.1053. But it says here find the percentage, so multiply by 100, and it's 10.56%. So 10.56% of runners will score more than 240. The 20% of runners with the fastest times qualify for the final. Assuming the race times are normally distributed above, work out the time needed to qualify in the final. So we need to sketch this out for a second, right? Because it's a tricky one. It says here 20% of runners with the fastest time qualified. So what most people would think is, okay, we're looking for like the area of like the top 20%. We're looking for this. But actually, if you're a runner and you run really fast, right? If you're a runner and you run really fast, that means you have a lower time. Right? We're dealing with a race here, so lower times means you're faster. So that means, right, 20% of runners with the fastest time qualify. So people in this region here qualify. Right? People in this region here will qualify. So this area will be equal to 20%. Right? Now we need to find out, well, what's the time that you qualify for, right? Well, if 20% of the fastest people qualify, what is that time? Well, I know the probability that Z is, this is some random number Z, or random Z score Z. But I know the probability that the Z score is less than that is equal to 0.2. Right? Now, this is obviously going to be a negative Z score, so this would be 1 minus the probability of the positive version. Equals 0.2. Probability that Z is less than Z is at 1. Right, 0.2 minus 1 is minus 0.8, then divide by the minus, we get 0.8. So if you reverse look this up on table, so we want to find out the Z score that gives 0.8. The Z score that gives me 0.8 would be so 0.8. That would be the closest one we have. Would be 0.5. So my Z score will be equal to minus 0.85. Remember, we're dealing with it below the mean here, so it has to be negative. So we reverse looked it up at 0.85. So I know x minus the mean all over the standard deviation has to equal this. So multiply by 12. 0.085 plus 225. X is equal to 214.8 seconds. Right? So if you basically score at most that or below this, right? If you ran the race in less than 2:14 seconds, you were in the top 20%, and that means you qualified for your race. Right. Let's have a look at this one here. In a school, all first years sat a common maths exam. The results in integer values were normally distributed with a mean of 176 marks and a standard deviation of 36 marks. The top 10% of students will go forward to a county math competition. Find the minimum mark needed to progress to the county stage. So this is like the opposite to the other one. Because now if you're in the top 10% of math scores, well, obviously you're in the top 10% of the highest scores, right? So this region here is equal to 10%. That means the region below it is equal to 0.9 or 90%. So we just need to look up now on my log tables where my Z score is equal to 0.9. And that would be when my Z score is equal to 1.28. When you look up into Z tables, then I need to now solve for X. So my mean is 176. My standard deviation is 36. So multiply across by 36 and then add on the 176. I'll get x is equal to 222.08. Right? So if you scored this mark or above, you were in the top 10% of you were in the top 10% of people in the maths test, and you were going to county. Right. Finally, this one here. The school awarded a certificate of merit to any student who achieved between 165 and 210 marks. Find the percentage of first years who received the certificate of merit. So they received between 165, right, and 210 marks. So basically, we're finding the probability that someone scored in between 165 and 210. So let's standardize it. So minus the mean being 176, 176 minus 176 divided by the standard deviation. Standard deviation is 36. 36. I now have the probability that Z is, put this in the calculator, yes, minus 0.31, and here we get 0.94. So sketch it out. Boom. This is 0. This is minus 0.31. This is 0.94. I'm looking for this area here. Well, this will be the area. This will be the area below 0.94 minus, now we need to find this little area here. Again, remember, when I'm dealing with negative Z scores and find the area below them, it's just 1 minus the positive Z score. So it's 1 minus probably the Z is less than 0.31, not negative 3.1. So 1 minus the probability that Z is less than 0.31. So that would be equal to 0.8264 minus 1 minus 0.6217. We look these up in your tables. And then we put this in a calculator, you'll get 0.4481, which is equal to 44.81%. So 44.81% of first years received a certificate of merit. Right, and then let's just do one more here. Right? In 2016, data on earnings were published for a particular country. The data showed that the annual income of people in full-time employment was normally distributed with a mean of 39,400 and a standard deviation of 12,920. The government intends to impose a new tax on incomes over 60,000. Find the percentage of full-time workers who will be liable for this tax. So you will be liable for this tax if you earn over 60,000. So standardize, right? So I see the words normal distribution and I see the word standard deviation, right? Mean. So these are telling me I have to use my Z scores, right? So that'd be minus 39,400 over my standard deviation of 12920, which is the probability that Z is greater than Z is greater than 1.5944, which is equal to 1 minus the probability that Z is less than 1.594. It's 59 really, right? Because when you sketch it out there, and you get here 1 minus 0.9441, which is equal to roughly 0.0559, is roughly equal to 5.6. So 5.6% of people in the country will be affected by this tax. Find this one here. The government will also provide a subsidy to the lowest 10% income earners. Find the level of income which the government will stop paying the subsidy. So they'll be paying for people who are in the bottom 10%. This here. So this area here is equal to 0.1. The probability that z is less than something, right, is equal to 0.1, but this will be negative, right? So I need to do 1 minus the probability that z is less than the positive version, equal to 0.1. Probability that z, right, you find the z score here. So this will actually be equal to 0.9. If you looked this up in the tables, so we get z is equal to minus 1.28, right? Because it has to be negative, right? Because we're dealing with the left of the mean. So x over standard deviation equals minus 1.28, minus the mean of 39,400, all over the standard deviation of 12,920 is equal to minus 1.28. Multiply across by that, and then add on 39,400. I get x is equal to 2,862.4 euro. So minus 1.8. Double check the number. 20,000. 22,862.4 euro. So if you earn more than 22,800 euro, you will not get this government subsidy, not being the bottom 10% anymore. Hopefully this video will help to you. Right, in the next video we're going to be looking at Z scores or for the sample mean. Right, so later. Bye.